Hello, everybody. So this is our first lecture from Math 4C. Maybe I'll write that. Math 4C, which is vector calculus. So you'll hear vector calculus called a few things. Calculus 3, vector calculus, multivariable calculus. All of these things are talking about the same thing, which is, the third semester of a calculus class, which traditionally covers functions of multiple variables and vectors in space and that kind of stuff. And so basically the way this class is organized is that we're going to cover, well, all of those things that I just talked about. So the Math 4C course covers vectors. And when I say vectors, it's going to be all of the operations and applications that you can do with vectors. Then we're going to cover functions of multiple variables. So instead of just having a function with, an x in it, like y equals f of x, you're going to have, f could be a function of x and y, or f could be a function of x, y, and z. So vectors, functions of multiple variables. What else are we going to be doing? So double and triple integrals, that's where our calculus is coming in. Double and triple integrals. Also derivatives, but I just left that off. I don't know why. And then finally, line and surface integrals. So we cover all of this stuff in a Math 4C class because that's what you need to deal with functions in space, basically. So a class like this prepares you to take classes in physics and engineering and stuff like that, where many different quantities that you're going to be dealing with are going to be represented as vectors. And many of the things that you want to calculate in physics involve either integrating over an area or a volume, which is what double and triple integrals represent, or integrating over a line and a surface, or a surface, which is what a lot of quantities in physics require you to do. So all of this stuff is what you do in any third semester calculus class, and we're no exception. So where do we start? So we start by learning about vectors and operations. And that means that this class actually starts out pretty simply. The first couple of lectures in this class are going to be very easy, which is nice. It gives you a couple of days to kind of ease into the class. But, it's rapidly going to become a pretty challenging class. A lot of the stuff that you're going to learn, though, is stuff that you already know. Like, would I say like double and triple integrals? Well, those are just integrals. You know how to do integrals. Line and surface integrals, those are just integrals. You know how to do integrals. Some of the stuff we're going to be doing with functions of multiple variables, like we're going to find maximums and minimums, you're going to find critical points and stuff like that. So this is all stuff that you've done in your first semester class and your second semester calculus class. And there's not that much new, really. It's just going to be new names for things, and you're going to have to, write them down and have those definitions handy in order to solve the problems. And really, you just need to be able to keep up with the class because falling behind is going to be disastrous. Like I said, though, we get started slowly, and so, you have a chance to start off, in a good way. So anyway, let's go ahead and get started with today's topic. We're going to be starting in section 2.1 in your book. So that book is the OpenStax Calculus Volume 3. So this is where you should look, OpenStax Calculus Volume 3. Right, Volume 3 for third semester calculus. And Chapter 1 is parametric equations. And so we do not start with that. We have enough to deal with just with starting in Chapter 2. All right, let's get started. So basically what I'm going to be doing in this lecture is I'm going to explain all the concepts you need from this section 2.1. And then after we're done, we're going to try to solve some problems in your homework just to make sure that there's nothing in the homework set that will surprise you, right? So I organized the homework based on sections. So everything in this lecture should prepare you to solve the problems. All right, so let's go ahead and actually get started now instead of just saying repeatedly that we're going to get started and then not starting. Okay, so what is a vector, right? We're talking about vectors in a plane. That's today's topic. So a definition of a vector. And this is a good definition, but it seems like a bad definition. So the definition is a vector is a quantity or mathematical object here that has a magnitude and a direction. Magnitude and a direction. Okay, so it's supposed to have both of those. So magnitude and direction. Okay, so the way we're going to talk about these things is as follows. Well, actually, let's what might be a vector? Like what quantities are a vector? So for example, a velocity is a vector. Why is it a vector? Why? Because you can't, it's not enough to say that somebody's velocity is, 30 miles per hour. 30 miles per hour tells you how fast they're going, but it doesn't tell you the direction you're going. And probably you remember from a physics class that a velocity also has a direction, right? It's not enough to say 30 miles per hour, that's a speed, right? 30 miles per hour is a speed. But if I said 30 miles per hour, due south, I guess I'll say, is a velocity. I didn't really have a good way to pick a direction. That's why I said due south. I'm just picking a direction. So the fact that this has a magnitude of 30 miles per hour and a direction of, in this case, due south, that's a velocity, right? And a lot of physical quantities have that kind of thing, a direction and a magnitude. And so, of course, vector quantities are used in physics all the time. If you took physics for A, you already know all this stuff. So if it has a direction and it has a magnitude, then how are we going to represent them? So a common way to represent them is to draw them on a plane, and you can draw them like this. So let me make a set of axes here. Right, so you have an x-axis and a y-axis. We're going to be dealing with three-dimensional vectors in the next section, so that's why I'm only drawing a plane here, not some kind of 3D shape. And then you can draw a vector just as a line segment with an arrow, basically, on here. So like if I put a dot right here, and then I put an arrow like this, that's a good way to represent an arrow. Yes. Well, it is an arrow. It's not a way to represent an arrow. It's a good way to represent a vector, right? So I have the vector, in this case, the vector v. Now, if you are going to draw it like this, then you can think of it as starting at a certain point, and we call that point the initial point. So like, arrows. I can't draw arrows pointing to arrows. That's just madness. Oh, well, I'm going to have to. That is where you start drawing it from this point to this point. This is called the initial point. The initial point. And where it ends up, which would be right here, that would be called the terminal point. Okay? And if you put dots in both of those places and you give those points names, like let's say we put this point right here and we call this P. And let's say I put a point right here and I call this one Q. Then you could refer to the vector as being a vector from the point P to the point Q, right? Initial point P, terminal point Q. And so there's a lot of different ways we could refer to that. We could say that the vector v, a lot of times you will write vectors like this. So you write the letter that you're going to use for the vector, and then you put an arrow over it. And you could write your arrows like this, but nobody ever does that because it's kind of awkward to write kind of this part of the arrow and this part of the arrow. And so what people tend to do is just write your arrows like this. So you'll see them that way. So the vector v, this is what I'm going to call the vector v. And another way to refer to it would be by saying it's the vector from P to Q. And again, you put the arrow over the top so you know that you're talking about a single vector here. So this would mean the vector with initial point P and terminal point Q. So this would just be a name, a different color here, sorry. So this would just be the name of the vector. And this name is also a name, but specifically the advantage to this name is you're saying what the terminal and the initial point is. The vector with initial point P and terminal point Q. You could say the vector from P to Q. So whenever you see this notation, you should know that it means you're starting at the P, you're ending at the Q, and what that looks like is like this on a graph. So we know a couple of ways to name vectors now. You can just give them a name, and you can just also label them as initial point and terminal point. Now, another key fact that you need to remember, first I'll tell you, then you can remember, is that we said up here in our definition of a vector that it's a quantity that has a magnitude and it has a direction. So the magnitude is how long it is, and the direction is, of course, the direction that it's pointing. Notice that we do not say it has a position. So it does not have a position. And that's important. So I'm going to write that. Key fact. A vector has a magnitude, which is its length. We'll define it better in a minute. So magnitude, which is length, and a direction, which is a direction. But no position. So what that means is that any two vectors that are the same length and point in the same direction are the same vector. So, for example, this vector, which I'm going to call V, and this vector, which I'm going to call W, and this vector that I'm going to call, I can't think of a third letter, it's impossible, U. Those are all the same vector, right? Because they are both pointing, they start in a corner of a box and then they go 2 boxes over, 1 box up. So they're all the same length and they all point in the same direction. So they're all equal. These are all the same vector because they have the same length and they point in the same direction. So you could use equality there. You could say that V, that's a V, is equal to the U, which is equal to the W. All right. And so, yeah, so they all are the same vector because the position doesn't matter. So I should have drawn it slightly differently. I should have put them in plane here. Oops, back that up, start over. So you have an X and Y axis. And if I go ahead and I just take these vectors, which maybe you can't see, and bring them down here, that, there. These are all the same vector, even though they're drawn in different places. Okay, so that is what a vector is. It has a direction, it has a magnitude, it does not have a position. So some of the homework problems are going to ask you which vector is the same as a given vector, and you're just looking for one that's pointing the same way, that has the same length. Very, very easy concept. So yeah. So the way you start out with the homework problems here, I'm not going to do a homework problem yet. I'm just going to write an example here. Is they tell you to sketch a vector. They say sketch a vector from initial point. So they use this language, initial point, P, which is 1, 1, to terminal point, Q, which is 8, comma 5. Right? And they make you do this. And the only real key to getting these problems right is to make sure that you don't get the direction the wrong way around. They have like a toggle for it. You'll see. So let's see here. 2, 4, 6, 8, 2, 4, 6. All right. So if you're trying to draw this vector, you're just going to go ahead and find the initial point, 1, comma 1, goes right here. That's P. You need to find the terminal point Q, which is 8, comma 5. So that is here, like that. And then you just draw that. So there you go. So that actually didn't quite make it to where it was supposed to go, did it? I don't know what happened. Oh, yeah, I do. Okay. I just drew that point in the wrong place. Okay, there we go. So 8, comma 5 and 1, comma 1. So that's all you're doing at first is just drawing vectors. Okay. After you can draw vectors, we want to know how to perform operations on the vector. And so let's see. I guess we'll use their definitions. What I want to do is I want to start writing vectors with numbers because you'll notice that like I don't have any numbers written here, and I don't have any numbers written here, and the book doesn't really start out with numbers, and that's why I'm just copying the book here. But I would like to, but I'm not going to. I'll copy the book. So once we can have an idea where a vector is, what it looks like, we're going to talk about adding vectors. So this is going to be a definition for adding vectors. So the sum of two vectors can be constructed graphically. Now, do I want to copy their entire definition or not? So I need two vectors. So let me get the two vectors. Move that over. So the two vectors are going to be v and w. V and w can be constructed graphically by placing the initial point of w at the terminal point of v. These are all vectors. And then what you do is the vector sum is going to be this. And then v plus w is the vector with terminal point, vection, words hard. the vector with initial point of the same as the initial point of v, and terminal point, the terminal point of w. This sounds a lot more complicated than it is. It's a lot easier to see this this way. So if I draw a little picture of, again, some axes, we don't really need axes here, but we'll do it. They're crooked, I don't care. So here's what we're talking about. So let's say you have a vector v like that, okay? And we want to add it to a vector w. So they say place the initial point of w at the terminal point of v. So this is the terminal point of v, so this is where w starts. So I'll get a different color. W can be like, well, it could be like a lot of things. I'll draw it like this. That could be w. And then the vector v plus w is the vector that starts here and goes to here. Okay, so it's basically the third side of the triangle there. And that's how you add vectors graphically. Now, it turns out that it doesn't matter which way you add the vectors, like which comes first, the v or the w. It turns out to not matter because you can think of it this way. Like if I have a v like this, and then I put the, where do I want it? Let's go like this. And w like that. And then this third side is v plus w, right? So I put v here and then w here. That's actually the same thing as if you put the vector, if you put the vector w first, and then you put the vector v. So this is w, and then this is v. So what's the difference? The difference is the tip of the arrow, the terminal point of v is at the initial point of w. And on this one, it's the opposite. It's the terminal point of w is at the initial point of v. And then you have w plus v here. And the thing is if you look at this vector here and you look at this vector here, they're actually the same exact vector, right? Like 1, 2, 3, 4, 5 straight to the right. 1, 2, 3, 4, 5 straight to the right. So v plus w and w plus v are the exact same thing. So we can observe that v plus w using our definition is the same thing as w plus v. It doesn't make a difference which one happens first. And that's because if you think about it, you could have drawn w like this, and you could have drawn v like this. And so this triangle and this triangle are basically the same. At least this side of the triangle is the same. Okay, so that's how you add vectors graphically. Again, we don't have numbers yet. Yeah. So vector subtraction is a little bit annoying. So vector, I'm not going to describe vector difference. I'm going to show you a picture. So vector subtraction here. So basically, if you want to find the vector, what vector? Let's say v minus w. So v minus w. First of all, you could think of v minus w. V minus w is also v plus negative w. That's one thing you can observe. Although we have not actually talked about how to come up with the negative w yet, so that's not great. But you could think of it this way if you want. And graphically, the way it looks is like this. So if you've got a vector v, and then you want to subtract w, then you put the w where the initial sides actually are, the initial points are the same point. So you put the w here. So that's different than addition, right? Because we're putting the initial points in the same place. And then it turns out v minus w is a vector from here to here. So let me do that. This is v minus w. Okay, and yeah. And that actually makes sense in terms of addition as well, because if you think about how we add vectors, right, you put them, you put the initial point of one of them, this blue one, at the terminal point of the other one, the w. And then if you add this one and this one, you get this one, right? So if you add the bottom side and the right side, you get this side, based on what we know from up here in these pictures. And if you do that, just thinking about it, w plus v minus w, right? W, which is this side, plus v minus w. If you think about just working through the symbols, w plus v minus w, positive w, negative w cancels, and you would be left with v, which is indeed this third side. And that's a way that you could check that you didn't draw this arrow pointing upside down. Because if you do the arrow upside down, then it would be this side plus this side equals this side, right? The one that's tip to tail, right? Right here, these two, those are the two that are being added to get the third side. So this is what vector subtraction looks like. It is a little bit tricky to visualize there. Okay. So let's talk about multiplication, I guess. Scalar multiplication. So we can handle addition and subtraction now. We can talk about scalar multiplication. So if k is just a constant, a real number, I'll say positive real number, and v a vector, then kv is the vector. It has the same direction as v, but its magnitude, right, its length is multiplied by k. Right? So just as a little example, 3v is 3 times as long as v. So that's not hard to understand, right? Like if I go like this, and if I say that's v, then 3v would just be the same vector, but 3 times as long. So like 1, 2, 3, 3v, like that. So just 3 times the length. And that's the idea behind scalar multiplication, which is multiplying by a number. That's what scalar means now. Yeah, so that's what scalar multiplication looks like. Let's talk about negatives. We didn't specifically talk about negatives, but negative of a vector is just pointing in the opposite direction. negative v has the same direction as v, the same magnitude as v, but points in the opposite direction. So what's that mean? Well, I mean, if that's v, that is negative v. So it's just the opposite direction. Okay? So what can we do now? So you can take the negative of a vector, graphically anyway. You can multiply a vector by a constant to make it longer or shorter. You can draw subtraction, although it's a little bit tricky to think about. Like you can put the v and the w there, but then you have to think, does the vector go this way or this way? So you have to get that right. And you can add vectors. Again, graphically, we haven't talked about numbers really yet in these examples here. So yeah. All right. So having said that, now let's talk about numbers. So let's see here. So here's how we get numbers involved. Definition. A vector with initial point 0, 0 on the plane and terminal point x comma y can be written in what we're going to call component form as v equals x, y. Triangle brackets. So we use triangular brackets there. Okay. And the x and the y are called the components of v. All right. So that is how we get numbers involved in our vectors. And that's actually a really simple way to do it, because if you have x and y here and you go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, right? So if you draw a vector like this, so start at 0, 0, and then you go to wherever you're going. So let's say here, and you say, what is that vector? Well, v is going to be whatever the terminal point is. So that's at 1, 2, 3, 4, 5, 1, 2, 3. So 5, comma 3. So triangle brackets 5, comma 3. And that's how we would refer to that vector. Okay. Now, what if we don't draw the terminal point at 0, 0, right? That's if it's at 0, 0. Well, what if we want to draw it, up here? How do we do that? And so that's the next thing we learn, which is going to be a component form of a vector. So, this is also another definition here. Erase, erase, erase. Definition. Or a rule, I guess. So if v has initial point, actually, let me do it this way so I can save some effort here. So if v is the vector from P to Q, where P is xi, yi, they use I for initial, and Q is xt, yt, t for terminal, then the component form of v, which is what we were just talking about, is v equals, and here's how you're going to get the component form. You subtract. So you subtract the terminal point minus the initial point for x, terminal point minus the initial point for y. So like this, xt minus xi, comma, yt minus yi. And that's how you do that. So, I mean, really, it's more simple than you think it is. If I come up here and let me find one, maybe. Do I have one? Yeah, let's take this one. So like, let's say we take this one right here, this vector, and drag it down to where we are. All right. So I'm going to say, let's call that v. And what are we doing? We're trying to find the component form of v, which was the vector from P to Q. So all you do is you just have to subtract the components. So like this Q here is at 8, 5, right? And this P down here is at 1, 1. So all you're going to do is you're going to say, well, v is just going to be subtract the x components. So 8 minus 1. And then for the y component, you subtract the y component. So we're going to subtract 5 minus 1. Like that. And then you get the vector 7, 4. That's the vector v. And if you think about it, it makes perfect sense, because if you count starting from here, that's 1, 2, 3, 4, 5, 6, 7 over to the right. So 7 over to the right, and then 1, 2, 3, 4 up. So 7 to the right, 4 up. So that's how you'll calculate the component form if you've got it just drawn on a graph like that for you. What else can we do? Just seeing if there's anything weird here. No, that's fine. Now we can do the magnitude of a vector. The magnitude of a vector, I'm going to write it in component form. So a magnitude of a vector v equals x, y is given by, so first of all, notation here. So magnitude, we write it sort of like an absolute value, but you use 2 lines. So this is the magnitude of the vector v. Absolute value, but 2 lines, 2 lines. And the way you calculate it is with the Pythagorean theorem, basically. Not basically, it is. So it's x squared plus y squared. Like that. Square root of x squared plus y squared. Okay, so why does that work? It works because, or it makes sense as a definition, because if you have, if this is your vector v, right, then you know that you've got, or you can think of it as having two, as being the third side of a triangle here. This is the x, this is the y. And then, of course, the length of the third side from the Pythagorean theorem would just be x squared plus y squared square root, right? So just writing it again. That's just the Pythagorean theorem. So we're literally just calculating the length of this line segment, and that's by definition the magnitude of a vector. So that's why you'll hear magnitude and length used interchangeably for vectors a lot of times. At least by me, you will. Okay, so that's the magnitude of a vector. Now we can talk about some of the operations, addition, subtraction, and stuff again, but now we can talk about them when you write your vectors in this form. Okay, so how do we do that? Well, here's how we do that. Definitions. So let v is going to be a vector. So x1, y1. And we need another one. W is going to be another vector. We're going to say x2 comma y2. And k is a scalar, which remember scalar means real number. So get used to that. That just means real number. And the reason we use the word scalar is just because vector means more than one quantity together here in a vector, and scalar means a single number by itself. So scalar is a real number, and a single real number and a vector means more than one component in a vector. All right, so we're dealing with two vectors here that I'm calling v and w, and we've got an extra number k. Why are we doing that? So we can talk about how to add them and multiply them. So we saw it graphically, but vector addition now can be written this way. So v plus w, how do you think you add them? Well, it turns out that all you have to do is add the x's and then add the y's. That's how you add. So add the x components, component by component, and then add up the y's, component by component. And that's how you make the vector where you add the vectors. So easy to do. Okay. What else? Well, we can talk about scalar multiplication. That was another operation we had. I'm not going to, by the way, I'm not going to do subtraction here because you already know that subtraction is adding the negative, which is going to be just the same as subtracting right here. So let's see here. K times v. We know that scalar multiplication just changes the length. How do you perform the operation? Well, it turns out that you just multiply the x and the y by the k. Like that. So that's actually pretty straightforward to do those operations. We kind of could have started with component form and then talked about graphical stuff, but we didn't. Somebody emailed me. I don't care. Let's do a couple of examples. So let's say, okay. Let's just say let v be 4 comma negative 5. And let's say let w be, I mean, it could be any vector. Let's say 3 comma 2. And let's just say find the following. So what are we going to do first? We're going to do v plus w. We're going to do v minus w. And we're going to do, let's say, 3v plus 5w, just to see if we can do it. Okay, and again, these are not, supposed to be any kind of trick here. We can just work these out pretty straightforward. So on this first one, we're going to do v plus w. So this is v, this is w. So you go the v, there's the v. We're adding it to w, which is 3 comma 2. And what should the result be? Well, you just add the x components. So 4 plus 3 is 7. And then you add up the y component. So negative 5 plus 2 is negative 3. So very straightforward to perform operations this way. We do v minus w. That would be 4 comma negative 5 minus 3 comma 2. And then this time we would subtract components. So 4 minus 3. 4 minus 3 is 1. And negative 5 minus 2. So negative 5 minus 2 is negative 7. Like that. And then if I'm calculating something like this, 3v plus 5w, you could write it out as 3v like that, plus 5w, which is 3 comma 2. And then you just take a couple of lines to do this. So the first thing you would do is multiply the scalar multiplication through here. So you would have 3 times 4 is going to be 12. So 3 times as long. 3 times -5 is going to be -15. Again, 3 times as long. Plus 5 times 3 is going to be another 15. And 5 times 2 is going to be a 10. Like that. And then you could add those up. So you add the first components, 12 plus 15 is 27. And then -15 plus 10 is -5. Like that. Okay. So what else can we do? Well, let's do one more. Let's find magnitude of v. And then let's also do magnitude of, let's say, 2w. Okay. So how would you write this, first of all? So you could write this as magnitude of v and just write magnitude and then your vector v. What is your vector v? Let's look up. It is 4, -5. And then how do you actually do that? Well, we have a formula for the magnitude involving the Pythagorean theorem, just square root x squared plus y squared. So you write that out, square root x squared plus y squared. Work that out. So it's square root 16 plus 25, which is the square root of, what is it? 41, is that what it is? Like that. And that would be your answer. I will have something to say about this after we do the next one. Let's calculate the magnitude of 2w. Again, magnitude is on the outside. We'll do that last. And then 2, and then your w. What's w? W is 3 comma 2. Like that. So you would work this out from the outside in. So first thing you would do is work out what 2 times w is. So 2 times 3 is 6, 2 times 2 is 4, like that. And then once you have the vector inside worked out, then you can calculate the magnitude using the Pythagorean theorem formula, which you would have to square the 6 and then square the 4. So we get square root 36 plus 16 this time. What's that going to be? Square root of 52. Right? Assuming I can add correctly. So that's that. So those are pretty much the operations that we can do now. We can write out some of the rules for vectors. So let's see here. One bit of notation that I don't think we mentioned yet is the zero vector. So it's kind of a definition, but not really. So this is called the zero vector. And by definition, it's the vector of all zeros. So it depends on whether you're in 2D or 3D or whatever. Zero components. Right, so in 2D, it's this vector. In 3D, which we haven't talked about yet, but it's going to be 0, 0, 0. And the only reason I'm writing that now, the only reason I'm writing that now is just to get across the idea that we just write 0 vector. We don't care whether it's 3 or 2, you just do whichever one makes sense where you are. So you don't need to say that it's the 2-dimensional 0 vector or anything like that. It's just 0, however many zeros you need to make sense for what you're doing. Okay, so then we've got some properties of all these operations that we learned. So properties. All right. So they use Roman numerals, but I won't. So first is u plus v is equal to v plus u. Okay. Um, doesn't matter which order you do it in. That's called commutative property. Okay. Um, then if you do vectors u plus v plus w, and you do those two first, the u plus the v, that's actually equal to u plus v plus w, where you do the v plus w first. That's called the associative property. Now, regular addition for numbers has both of these properties. So this is actually nothing new. It's just you didn't technically know that vector addition had the same property as regular addition. And same thing here. You didn't know that vector addition had the same properties as regular addition. All right. If you take a vector and you add the zero vector to it, what do you think happens? You just get the same vector back. They say that's called having an additive identity. They say additive identity property, but that's the idea. You add zero and nothing happens. Next thing is if you add u to the negative of itself. So like what's 1 minus 1? 0. 2 minus 2? 0. Right? So if you add something to the negative of itself, you're just going to, I keep writing theta. You just get the 0. U minus u is 0. That would be the additive inverse property. Just going to write additive inverse. Then you get some properties for scalar multiplications. So what we were doing so far was u, v, w for vectors. And now what I need is r and s are scalars, numbers. So if you do r times s times u, so you see why we want to use the arrow, right? So you can tell that u is a vector, but r and s are not, just by having it written down for you. I should say this as well. When you handwrite vectors, you use the vector symbol over it, right? The little arrow. But when the book writes vectors, they don't. They use a bold U, and that indicates a vector. You'll see that they don't use an arrow. But when you handwrite it, you use an arrow. Okay, so what's going on here? Number r times number s times vector u. So a number times a number times a vector. How does it work? Well, it turns out that you could do it that way, or you can multiply the r and the s and then multiply it by u. And that's another associative property, right? It doesn't, like, associative is where the parentheses are. If you can move the parentheses and the result doesn't change, that's an associative property. So this is an associative property. All right. Then we have a distributive property. If you add up two numbers and then you multiply them by the vector u, that is the same thing as if you multiplied the first scalar times u and the second scalar times u, and then you added those, right? So that's distributive, right? So r times u, s times u, distributive property. Okay, and again, real numbers already have these properties. So we're just writing down the properties that vectors also have. So that's all just the same rules that you pretty much already know, but you don't know them for vectors technically. So what if you add two vectors and then multiply by a scalar? Well, again, it's just a distributive property. So the r times the first one and then the r times the second one. That should be a v. Right? So you're just doing r times u, r times v. Just like this was r times u, s times u to get this. So So that's another distributive property. All right, almost done. Last one is if you take the number 1 and you multiply it by u, what do you think you get? You get u. And I have no idea why they do this, but they didn't give it another number. They wrote 0 times u is the 0 vector. So that's the multiplicative identity. And this is 0 property. Oh, I said multiplicative identity. And this is the 0 property. Right, multiply a vector times 0 and you get the vector 0, 0, 0. Okay, so I don't really want to prove these, but I'll prove one of them just so you can see that the proofs are actually very simple. So let's prove the first one. U plus v is actually equal to v plus u. And it all comes down to the fact that regular numbers already have these properties. So what's the proof look like? You say let u be x1, y1, and v equal x2, y2, right? So you have your two vectors, and then start with what's on the left here, which is u plus v, is equal to, we know how to add those up, right? We have a rule. It's x1 plus x2, comma, y1 plus y2. But then you know that for regular numbers, addition, the order doesn't matter, right? So property of real numbers, so using a property of real numbers, I can switch the order of addition here. So that's not cheating because this property for real numbers, we assume we already know is true. Do the same thing for the y's. I put an extra plus here, it looks like that. So I'm just switching the order, the y1 and the y2. And then now you can back it up. So like just like this is defined to be this, like the u was the 1s and the v was the 2s. Well, now the 2s come first. So this is equal to x2 comma y2, which is v, and x1 comma y1 is listed second, so that's the u. So what did we do? We showed that u plus v is v plus u. So that's what the proofs look like for all of these. They're just very, very simple proofs. And that's why we don't bother, or I don't bother. You can prove them all yourself for fun. You have lots of time. Okay, so let's keep going here. Oh man, I think we have like one more thing I think that we have to do, and then no, two more things we have to do, and then we can be done with this video here. Okay, so there's a trig relationship that you can use. So trigonometry for component form. And you kind of need to know this, but I feel like a lot of people get away without knowing this, but your life is a lot better if you do know this. So let's draw a picture here. So let's draw this vector here, and let's say that this is v. Okay. So I just have a vector. Now it turns out that you have these two sides of a triangle that we talked about those when we were making when we were talking about the magnitude of a vector, right? Well, it turns out that if you use a little bit of trigonometry, you can draw an angle here and call it theta. And it would turn out that this side of the triangle, the length of the side is the magnitude of v times the sine of theta. And it turns out that this side of the triangle is the magnitude of v times the cosine of theta. And this relationship holds. And it turns out the third side of the triangle here, I called that vector v, which it is. I should actually not have erased it. Call this v, I'll put it up here. But it turns out that if you wanted the length of this side, the length of this side is the magnitude of v. So there's this relationship between this angle, this side, and this side. Okay. And you can use that for various things. Okay. So here's what you could use it for example. They say find component form, find the component form of a vector with magnitude 4 that forms an angle negative 45 degrees. That's a percentage, Greg. That's not right. 45 degrees with the x-axis. Okay, so this is where you would want to know this form right here, because if you can calculate these two sides of the triangle, that's very helpful here. So I'll draw a picture so we can see what we're talking about. Right, so what we're talking about is negative 45 degrees. If you think about just standard position, negative 45 degrees is like 45 degrees down this way, right? So if you go 45 degrees down here, you're talking about this, right? A 45 degree angle down. Okay. And then what you want is a magnitude of 4. So the vector that we're looking for is in this direction. So it starts here, goes this way, like that. And this is the vector that we're looking for. I'll call it v. Okay. So that's what we're looking for. And you could do complicated things to figure that out. But if you remember this, it's not that complicated, because this is your x component and this is your y component. And then you'll be able to figure out this without much work. You would just say, basically, we know this. We know that the vector v should be the vector whose first component, x component, is magnitude of v. Is it x or cosine? Cosine theta, right? Is this one. Sine theta is the y value. So cosine theta, comma, magnitude v, sine theta, like that. So if you fill in your numbers, you've got everything you need, because we know that the angle is negative 45 degrees, that's your theta, and we know that your magnitude is 4, that's your magnitude of v. Right? So you just fill in those numbers. So this is your magnitude v, and this is your theta. So what you have is 4 cosine negative 45 degrees, comma, 4 sine negative 45 degrees. And then you just work those out. And you need to do this in an exact form. You cannot, you can't just use a decimal. The computer will not take that. So you would actually have to calculate what the cosine of negative 45 degrees is. So you would have 4, and then you know cosine negative 45 degrees from your trig. That's going to be what? Square root 2 over 2, right? And then over here, 4 times the sine of negative 45 degrees. So that's 4. And then the sine of this angle, is going to be negative square root 2 over 2. Like that. And then if you simplify by canceling the 4 and the 2, you end up with 2 square root 2, negative 2 square root 2. And that makes sense because that at least is in the right quadrant, right? Because x is positive and y is negative. So positive x, negative y. So what we're looking at here is this and this. This is 4 times square root 2 over 2. And then this was 4 negative square root 2 over 2. And so it's that triangle there. But you don't need to draw the picture or even think about the picture if you memorize this, right? You memorize this and then you can just fill in the numbers. You don't have to draw a picture if you don't want to. You don't need the picture. Okay. All right. Finally, last thing. We're an hour and 5 minutes in. So this is our last topic. It's not our last topic. We have two. How do we have two? And we're going to talk about unit vectors. That's next. There's always so many things to go over when you're like in the introductory sections. So unit vectors. So a vector is a unit vector if its magnitude is 1. In symbols, unit vector, V is a unit vector if magnitude V equals 1. Okay. Now, the thing about unit vectors is you can make a unit vector. How do you make a unit vector? So a unit vector u in the direction of v can be found by unit vector u. And basically what you do is you do 1 over the magnitude of v, and then you times v. And that probably seems a little bit complicated, but it's not complicated at all. You'll see. Like, watch. Example. Find a unit vector in the direction of 3, 4. Okay, so if you want to do that, what you do first is step 1, find the magnitude of that vector. Right, that's the length. So you do magnitude of 3, 4, and that's where you use your Pythagorean theorem, 3 squared plus 4 squared. So you end up with square root of 9 plus 16, which is 25. And lucky you, it came up 5. So came up to be an even number. You usually do not get that lucky, but we did this time. So then what you do is you basically just divide the vector by that. So then you multiply vector by 1 over magnitude v, basically. So what you do is you go 1 over the magnitude of v times v is simply going to be, in this case, 1/5, right? Because this is the magnitude of this vector is 5. So that's the magnitude. And then you multiply by the original vector, which was 3, 4. So what do you get? Well, if you multiply this through, which we know that that's how scalar multiplication works, you get 3/5, 4/5. Okay, so that's all you have to do there. And then an additional thing that you may do is sometimes they say find a vector with magnitude like 10 in that direction or something like that. So bonus question. Find a vector with magnitude 17 in this direction. Well, how do you think you do that? Well, that's actually very, very simple, right? Because by definition, what's the length of this? It's called a unit vector, right? What's a unit vector length? A unit vector length is 1. So if the length of this vector is 1 and you want it to be 17, you would just multiply the 17 times the vector with length 1, and then that would give you a vector with length 17. So that's the idea. So you just, so if you multiply a unit vector, which is length 1 by definition, by 17, you can change its length to 17. So very simple. So the answer in this case would be 17 times this, which is the unit vector. Like that. Okay. And you can multiply that out if you want. 17 times 3, what's that? 51. So like 51 over 5, I guess. And then 17 times 4, what's that? 34 and 34, so 68 over 5. So this should have length 17 then, because this was a unit vector and we multiplied by 17. Okay. I believe we have one thing left to do, which is actually very simple. So the last thing is standard unit vectors. So basically, we give two vectors names. So basically, we give two vectors. In 2 dimensions, it's 2. In 3 dimensions, it's going to be 3. We give two vectors special names. So one of them is going to be I. So it's a vector I. So basically what you do is you write an I, and then you replace the dot with your arrow. So I is vector 1, 0. And then you have a j, which is 0, 1. Okay. And depending on what branch of science you're in, it's possible that these don't have these same names. Okay. But this is what we're using. I is 1, 0. J is 0, 1. Okay. And what you can do with that is we can write it in, what do they call it? What do they call it? They just say using standard unit vectors. So what they do is something like this, right? I could say like write, let's say 5, negative 9 as a combination. I don't know if that's the wording that they use, but I'm going to use it as a combination of standard unit vectors. Okay, now it's really simple here. This is like a million times easier than you think. So here's the idea, and then we'll just do it. So idea. So 5 comma negative 9. You can think of the 5 as being as coming from 5 comma 0. So you can think of this as coming from the vector 5, 0 that gets this first component. And then for the second component could be negative 9. So that is 0 comma negative 9 like this. Right? This is true, right? 5 negative 9 is 5, 0 plus 0 negative 9. And then this one right here looks like the I, and this one here looks like the J. The difference is the 5 and the 9, right? So you could write this as 5 times 1 comma 0. And you could write this as negative 9 times 0 comma 1. Or minus 9, 0 comma 1. Right? And then what you can do is you can say, well, what is this? It has a name. 1 comma 0, we gave a name, it's called I. So this is I. And this one here is called J. So minus 9J. Okay. Now, I said that that's the idea. That's actually 100% of the work, right? So once you've convinced yourself of how this is supposed to work, you can easily translate it back and forth. So the punchline is this. If you see 5 comma negative 9, you could say that this is 5I plus, or minus in this case, minus 9J. So this form or this form, they're actually are just two forms of writing the same vector. And they use this a lot. I don't like it at all, to be honest. I like this. I don't like writing this. But it's basically just two different ways to write the same thing. Okay? So they will have you use that in the homework. Okay. So I was going to do homework at the end of this, but after an hour and 18 minutes, I think we should save that the second video. So that's it for now. Good luck on the homework. I think you can do it. If not, then, there'll be more videos coming in the future. Have a good day.